So in this video, I'd like to go over the Pythagorean theorem. It's a well-known theorem that everybody knows. They probably learn it somewhere in grade school somewhere. But the Pythagorean theorem, in the Pythagorean theorem, it's basically you have a triangle, and this is length A, and this is length B, and length C, and this is basically a right-handed triangle. Pythagorean theorem basically says that c squared is equal to a squared plus b squared. Now, there are literally dozens and dozens of these proofs for showing that the Pythagorean theorem is true. But for example, you probably took it in high school in terms of Euclidean geometry, and you did triangle similarity laws. And after you finished that, right, you found that there's a proof that basically we can take similar triangles and eventually show that c squared is equal to a squared plus b squared. And that's nice because it was actually to support your understanding of Euclidean geometry, and so when you took it in high school somewhere. But in reality, I like the following proof. It's not anything special, it's just I kind of really like the proof. It's simple, and you can teach somebody very quickly that this must be true. And the idea is that you have to have a little understanding of a little bit of algebra and areas. And what's really strange is that we're using areas, and we have an intuitive understanding of what an area of a rectangle and a triangle is. And that intuition, right, helps us actually solve this problem. And it's a kind of a little problem. It's problematic also in the sense that we don't have a, I'm not giving you a definition of what an area is, but I'm just using it from your experience. And the idea is that if somebody gives you a triangle of A, B, and C, what I'm going to do is construct a large square. And this square, right, I basically construct a smaller inner square. And this inner square, right, will have basically, so here's my inner square. And I'll just show you this like similar points. And what I do is I cleave up the square into points. And each point, right, represents here's your A and B length. Here is your A and B length. Here is your A and B length. Here is your B and A and B length. And what I do is basically draw a smaller square, and that's inside, lying within this triangle. I'm sorry, within this rectangle. So, and we call this length, right, C. Okay, so we know this, so if somebody gives you A, B, and C, we can actually construct a large square with lengths A, B. So this is a large square. So I'll make sure that this is correct. And I haven't really drawn this properly, but because my drawing skills were very bad. But that's fine. This is supposed to be a quick proof so that you can prove to yourself that, so this length is C, this length is C, this length is C, this length is C, because all these triangles, ABC, 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 are cornered. So we ask ourselves, what is the area of this outer rectangle? Well, it's the length of this squared. So this is really A plus B squared. So what is this area equal to? Well, it's equal to the area of these triangles, 4 triangles. And so what's the area of these triangles? It's base times height times 1/2, which in this case happens to be 1/2 BA. So this is the area of these 4 triangles, plus the area of the inner square, which is C squared. So we can expand on both sides. This is really A squared plus B squared plus 2AB. So hopefully you remember how to expand in terms of first, outer, inner foil, if you want to call it. And then here is 2AB plus C squared. And if you look carefully, this 2AB disappears, and we get A squared plus B squared is equal to C squared. So this is Pythagoras' theorem. It's very quick. It's not much heavier math than just looking over areas of triangles and rectangles or squares in this case. But what's really cool about this is, right, it's quick. I just had to expand it twice, and you can write this very quickly, prove to somebody that Pythagorean theorem is not something very abstract, but you can really construct it very quickly from a basic understanding of areas. What's wrong with it, right, is that we're assuming that there is a concept of an area, which we haven't really proven. So, but it is a simple proof, assuming your intuition of areas are correct, about an area of a rectangle, area of a triangle.